So how is software-defined networking in OpenFlow different from today's model of networking? Well, let's look a bit at an Ethernet switch. So we have an Ethernet switch. It has ports, Ethernet ports. It has lights, activity lights, error lights. It has software that's running on the switch. It's usually called firmware. And the switch implements a number of features. Maybe it supports VLANs, maybe it supports access control filters or tunnels, or other features that you find useful. And this Ethernet switch appears as an appliance. So it's a standalone device. It has these features. So let's look under the covers of this Ethernet switch. The firmware, or the software, is really an embedded operating system. The vendor has included software running on that embedded operating system to provide the features. Another name for this embedded operating system with its features is the control plane. There's also packet forwarding hardware in an Ethernet switch. So there's special hardware. Sometimes it's custom designed by the vendor. Other times there are companies that specialize in making high-speed packet processing chips. An Ethernet switch might have custom chips made by the vendor. It might have commodity chips that are designed to do this. In some cases, they have a mix of custom chips by the vendor as well as commodity chips. This high-speed part of the Ethernet switch is called the data plane. So in a more simplified view, you have a control plane, which is mostly software, and you have a data plane, which is the high-speed forwarding hardware in an Ethernet switch. The role of the control plane with respect to the data plane is the control plane actually configures the data plane. So the data plane on its own would not know how to forward packets. So the control plane essentially puts rules in special memory hardware in the data plane, and then the data plane is driven by those rules and processes packets at high speed. The control plane maintains something called the forwarding table for the data plane. So the data plane is, again, table driven, and it has something called the forwarding table, and its high-speed hardware interacts in a very efficient way with this forwarding table to make the packet forwarding and handling decisions. So the role of the control plane is to actually configure that table. The role of the data plane is to use that table to implement the features to carry out the packet forwarding and handling. Let's take a closer look at the forwarding table. So a forwarding table is what it sounds like. It's a table. It's special memory that's in the high-speed data plane section of the switch, and it has rules. And if you looked at the rules for the forwarding table of a basic Ethernet switch, you might see things that say the equivalent of, if the destination address is unknown, flood the packet. If the destination address is known, output the packet to the correct port. For a layer 3 capable Ethernet switch, you might see rules that say if the IP address is a certain value, then drop the packet. Or perhaps if the TCP port is a certain value, mirror the packet to another port. Maybe it even says if the IP address is a certain value, rewrite the packet. For example, in the case of a network address translation gateway. Again, the control plane in a regular Ethernet switch maintains this forwarding table, and the forwarding table defines the behavior of the high-speed data plane. In an OpenFlow switch, this forwarding table is known as the flow table. In the OpenFlow paradigm, the forwarding table, the high-speed forwarding table in the data plane section of an Ethernet switch is called the flow table. So let's go back to our switch again. We've got an Ethernet switch with a control plane and data plane, and we talked about the roles of these two parts of the switch. Now imagine redesigning the architecture a bit and separating the control plane from the data plane physically, not just the logical distinction in their roles in the switch, but actually physically separating them. So I have some device that's acting as the control plane, and then I have some device that's acting as the data plane. I can use the protocol OpenFlow to allow the control plane to control the table entries in the data plane. So remember, there's this table that drives the behavior of the data plane. In an OpenFlow environment, we call that a flow table. And we can use the OpenFlow protocol to take a control plane running on a server and to control that table running on the high-speed portion of the switch. And the control plane in the language of OpenFlow is called the OpenFlow controller, and it can manage the tables in many switch data planes. So in a campus environment or an enterprise environment, you may have hundreds or even thousands of switches, and their data planes, their flow tables, are controlled by a central controller. That controller is based on a server platform. It's also a development platform, so rather than the vendor having to develop features in the firmware that runs in the embedded system on an Ethernet switch, you can develop software that runs on a server. Much better development, much more open development platform to implement features in those switches. It also allows you to introduce new features across your entire network just by loading new software in the control plane on the server. Let's suppose you wanted to implement a new feature in your network to better support employees who are bringing their own device to work. That feature could be defined in software on the OpenFlow controller, and that OpenFlow controller would provision features in the switches by manipulating the table in their data plane to support the network behavior that you're looking for to support bring your own devices.